So, as already many times told, we need the infinitesimal analysis in particular to understand then numerical methods, just to estimate errors. And that's everywhere. When you work with data, you want to estimate errors you are doing. And so let's have a look at numerical derivatives as a simple and easygoing illustration of the basic ideas behind. And that's a direct application of the Taylor expansion and the remainder there. So what do we want to do? So you see, we know that if we want to discuss the derivatives, so what should it be? So it's just something like fx plus v minus fx. So that's the growth of the value when we let the argument grow, and we divide it by v. So we have the relative growth, right? And now we go with v to 0, and this is the derivative. So if we want to have something reasonable at hand, so what can we do? So we can imagine that we have some standard increment, say h, all the time the same, and we shall have points which will be one after the other always got by adding the h, right? So xi will be, x0 will be a, and xn will be b, some end of the interval, and then we cut the interval into n pieces. So it will be the length divided by n will be h, right? So that's how we do. And now the Taylor theorem says how the value looks like. So it's the value in the ith point x plus h times the derivative plus h squared over 2 the second derivative, and so on. And if it's plus minus h, then we have got either plus or minus, and this depends on whether it's the odd or even power of h. So if there is an odd power of h, it's plus minus. Again, if it's even power, it's just always plus, independent of whether we've got plus or minus there. And so we can just have a look what the remainder will be, and the remainder we know what it is. It's just, if we write it up to the kth power of h this way, then the k plus first term will be the remainder, except the remainder will be not in the original point xi, but we shall have to take, say, the maximum or the bound for the k plus first derivative all over the interval of interest, x minus h or xi plus h, right? So the k plus first derivative, if it's continuous, we know it will be always bounded by constant on the whole interval ab, and therefore we can expect that only a small error will be expected in the approximation by the Taylor polynomial, and that's what we would say, that the error is big O of h k plus 1, right? So that's the error. Right, so that's where we were already, and now we can go on, and we just write it shortly as fi plus minus 1. So that's how it is. And now what we do is just we take the differences to approximate the derivatives here, right? So we can either take what's called the central difference, so it's the I plus first value minus I minus 1 value, and then the length of the interval we look at the difference is 2h. And you see that if we do it this way, then of course in both the fi's will just always be there, so they are gone. Then there will be the fi dash, because it's twice, right? So once we have plus, once we have minus, but the minus will go with minus, so it will be 2 times plus. So the 2's are cancelled, and only the derivative remains. And then the next one is h squared. So this one will be always with plus. So this guy just goes completely. That will be not appearing. And the next one will be the third one, and divided by 2h, you see, so it just, that will be only 3 factorial here then, and there will be the third derivative, but it's h squared. So you see that the so-called central difference, which we compute here, approximates the derivative in the asymptotic precision of big O h squared. Whereas if we do only one side differences, so fi plus 1 minus fi, then you see it will just be fi dash as always, but then already the second one stays there because we just subtract only fi, right? So this is subtracted and all the rest stays. So you see that it's just one order verse asymptotic approximation. It's here coming with h, not h squared. And the same if we go to the backwards, that's the forward difference, that's the backward difference. So if we do it the other way around, then we get again just the value, and it will be minus the same thing as here, right? So the error will be then again asymptotically of the first order OH. And this is what's written here in the theorem, and it says the asymptotic estimates of the error. So what's due to say is that actually it doesn't mean that always the central difference must be better than the forward or backward differences, because you see it might be that for practical use, so remember today I was showing you the smooth function defined by the exponential, which had all the zeros at the beginning, nothing but zeros there in all derivatives, but the derivatives as such were jumping and wiggling very fast and very much already for low orders. So it might be you have functions where the first derivative is quite neat and close to zero, so the function is sort of growing very slowly, but the second derivative will be extremely big, because although it will be all the time small, the first derivative, so the slope of the tangent, it may be wiggling very fast. And so the actual choice must be always taken corresponding to what problem you are solving. So that's it, right? So this is what we had to say. Well, we can do the same for second order derivatives and so on for higher order derivatives, right? So for example, for the second order derivative, a very good idea is to take the second order difference. So you add the two neighbors, the values, and you subtract 2 times the center, right? And that, if you look back how the Taylor series was, so we just add the 2 neighbors, so it will be one with plus, one with minus, so this one will go there, and we subtract 2 times the very value of fi, so the fi will go as well, right? So it will be 2 times plus and minus 2 times this guy. So what we are then left with is exactly what we've got here. So it's the second derivative, and then it continues with h squared over 12 times the, so because it will be the fifth order term in the Taylor series, summed together this way will appear here, and well, actually the fourth order term appears as the first one and is divided by h squared, so therefore you have got h squared here as well, and that's it. So that's the so-called second order difference, and you see that it approximates the second derivative asymptotically with the precision big O of h squared. So this is just the first indication of how the estimates in numerical analysis could look like. I will not go into much detail through the book here, but at least something. So that's finally all for this week, and have a nice rest of weekend.